Another useful lens equation is what's called the LensMaker equation. It is in sort of the equation that someone who's trying to make a lens have to use. For example, opticians at factories that make contact lenses, for example, or opticians that make glasses for prescription glasses. Now, the LensMaker equation is here. 1 over f is equal to the index of refraction of the material making up the lens, and G is for glass, whatever material we are using to make the lens with. And then n sub m is usually 1, because usually most of the lenses we make, they are intended to be used in an environment where they are surrounded by air. However, for example, for a lens that's going to be used in water, n sub n has to be the index of refraction of the medium. That in that case, that would be the index of refraction of water. So n sub g is the index of refraction of the material of the lens, and n sub m is the index of refraction of the medium surrounding the lens. And then multiplied by 1 over r1 minus 1 over r2. And r1 and r2 are the radii of both sides of the lens. For example, this side is a curved side that's going to have a radius. Its radius is going to be r1. And then, so the first side that the light is going to meet when it comes into the lens is going to have a radius r1. And then r2 is going to be the radius of the other side. Okay, now this equation approximates again a thin lens. It does not take into account a possible thickness of the lens d. I took these pictures from Wikipedia where they show the d. If you go to that website, for example, you can find another expression where you have another term added to account for the d. I'm not going to get into it here. We are going to use the thin lens approximation where d is essentially 0. Now, one thing important about this lens is figuring out the signs of the radii, r1 and r2. It's a little tricky, but not very complicated if we pay attention to it. Okay, this is the convention. I like the way it was written on this website on the bottom, so I took it from there. It is the radius of curvature is taken to be positive if light, after passing through the surface of the lens in question, can pass through the center of curvature of that surface. What does that mean? Okay, for example, I have light coming in here. Okay, as the light coming in here, okay, it's going to meet this surface. Now, what's the radius of curvature of that surface? This is the center for that surface. R1 is the radius of curvature. Now, what they say, if light, after passing through the surface, so now after passing this surface, if, I'm using a different color since it's important, if it can pass through the center of curvature. Now, light have passed here, can it pass through that radius? I mean, through that radius. In this case, yes. If it does, then R1 is positive. If it does not, then R1 is negative. Let's take in this particular case, I'm going to erase whatever I wrote for R1 and for that surface. Okay, now let's consider R2. So when are we going to meet the surface for R2? This is the surface. What's the radius for that surface? That's the radius for that surface. Now, after passing through the surface, now we are going to pass the surface. In color like last time, this is when we passed it. If we are going to pass through the center of curvature, but where's the center of curvature? It's here. If we are going to pass through it, then R2 is positive. If not, R2 is negative. So in this case, we are not going to pass through it, so that means our R2 is negative. Okay, that's the rule. Let's look at some examples. It's there from the same website. I like the examples. So this is our lens in blue in this case and in this case, and in here it is in pink or whatever color you call that. Okay. Now, he's showing here the radii for each of the lenses. He's given us the radii, R1, R2. I changed the colors to show that this one pertains to the first one, this one pertains to the second one, and this one to the third. Now, we have the same indices of refraction for all of them. Ng equal 1.5, that's the index of refraction of the glass, and the medium is 1, is air. Now, if you consider the blue lens, so that's what we have, our blue lens. R1 is 5 centimeters, R2 is 10 centimeters. Now you have to decide which one is positive, which one is negative. Since I did the lens just like that a minute ago in the previous screen, I'm not going to go through this one. Let's go through the last one, and I'll let you try by yourself the middle one. Let's go through the last one. So here is our light. It's going to meet this surface. Okay, the surface, its radius is R1. So after passing through that surface, guess what? We are going to be able to pass through R1. So R1 has to be positive in that equation. Okay, now let's consider the second surface. This is the second surface, R2. As light passes through that surface, and then guess what? This is the center of curvature for that surface. Light is going to be able to pass through it after it passes through this surface. So that means R2 is also positive. So when we write our thin lens equation, in that particular case, both R1 and R2 are positive. So just plug them in, plug Ng and Nm like there, plug them in, you should be able to find a focal length of minus 13.3 centimeters. Now the power here, I kept it since he used it. The power, and I think I'm defining it later, is what we have as 1 over the focal length when F is expressed in meters. And the unit that we are using there is what's called diopters. Okay. So that's just another way to measure the focal length, and it is the unit that's usually used by opticians. Okay. Just one thing to as a reminder or as a pointer, lenses are going to take many shapes and forms. There is what we call the biconvex lens. You know, and the thickness here is going to depend on the lens in question, and that pertains to all lenses here in the picture. So a biconvex lens has 2 convex sides. Then we have what's called plano-convex lens. Now, in a plano-convex lens, what do we have here? One of the sides is flat. If one of the sides is flat, the radius for that side is infinity. Okay, and then we have what's called positive meniscus. Positive meniscus is a lens that has one side, one side that's convex and one side that's concave. But the convex side has a smaller radius than the concave side. Okay, the positive is telling us about the focal length of that lens. Now think about contact lenses. So you might want that side to be curved, but then you still want a convergent lens, so you make the other side more curved. And then you have what's called the negative meniscus. Negative meniscus, same kind of thing, it's a curved side, but in this case, the concave side, it has a smaller radius than the convex side, resulting in an overall negative focal length. And then, of course, we can have a plano concave lens, one side having a flat surface and the other side is concave. And that, remember again, the flat side is going to have a radius of curvature that's infinite. And then we have the biconcave, the one that we've been using whenever we graft a divergent lens. All of these lenses, we use the LensMaker equation to be able to find their focal length. Again, assuming that they are thin lenses and the thickness of the lens is too small to account for.